Good morning, everyone. Welcome to the DLD class. In today's class, we will discuss about digital logic families. Okay. So, what is a digital logic family? In many applications, many electronic applications, you must have seen different chips. Okay, or what we call them as integrated circuits (ICs). So a group of ICs which are compatible to each other. So by compatible, we mean they have same logic level and they have same voltage performance characteristics, and they are fabricated using the same circuit configuration. They are called as logic families. For example, we can say the family of human beings, family of dogs, family of cats. Similarly, families of ICs which have similar operating characteristics. That doesn't mean they are all doing the same job. We are saying that they are fabricated from the same technology. Okay. So how do we define the characteristics and how do we characterize them? Like, what do I say that? How do I say that they are belonging to a same family? For that, there are many aspects to consider: the number of inputs that can be connected, the number of outputs that can be connected, what is logic level 1, whether it is high plus 5 volt or minus 5 volt, the range of voltages that we call as logic 1 or logic 0. There are many such characteristics which help us to say what is a logic family. However, apart from this, the more important aspect that we must consider here is how the circuit is constructed. Okay, we'll see a very simple and small example here. Okay, you see there is a switch connected over here. Okay, you have 5 volt power supply and there is a switch connected here. As soon as I connect this switch, when I push this switch, what happens is this output gets shorted to the ground. Hence, in effect, when I am giving logic 1 at the input, the logic output 0 appears at the output. That means whatever input I am giving here, opposite of that is appearing at the output, which is the typical operation of an inverter. Hence, in here, the switch is acting as an inverter. Similarly, when I remove this switch or I give 0 signal, the plus 5 voltage starts appearing at the output and the output goes high. That means when I am taking away the value, that means when I'm giving 0 value, the output actually becomes 1. Again, it is the operation of a basic inverter. Here we are using switch as an inverter. Can I achieve the same thing using a diode? Yes. Here, instead of a switch, we have connected a diode. As soon as I give logic 1 here, so this device becomes reverse bias and the voltage flows towards the here. The current flows through here. However, if I connect it to ground, this is a least resistance path, so the current will flow from here to here, and using this I can use a diode as an inverter. Here you have a BJT, bipolar junction transistor, in a common emitter configuration. Here once again, once we give some positive voltage over here, the base emitter voltage is forward bias, the transistor will turn on, it will act like a switch, it will get short circuited and the output will go down from here. That means application of plus voltage here will result to 0 voltage here. Similarly, application of 0 voltage here will give some plus voltage here. Hence, in here, BJT is acting as an inverter. Which brings us to a very interesting point. I have switch as an inverter, I have a diode as an inverter, I have a BJT as inverter, and in fact, if I consider another form of transistor, which are unipolar transistor, that means PMOS and NMOS transistors, we can see that When this input voltage is 0, PMOS is on, and the current flows through here, and the output becomes, the capacitor charges, the output becomes 1. Similarly, when we give 1 here, the NMOS transistor is on, the capacitor discharges from this path, and the output becomes 0. So this is a complementary metal oxide semiconductor as an inverter, which brings us to a very important conclusion, that despite looking for so many different types of implementation, each of these circuits are performing the same task. So the question is, which one is the best? To come to that answer, we must compare these circuits based on certain characteristics. These characteristics will help us to define whether our circuit or the inverter or the particular design methodology is helpful to us or not. Hence, we must consider the characteristics of digital ICs. The various characteristics of digital ICs that are used to compare their performance are speed of operation, power dissipation, figure of merit, fan out, voltage and current parameters, noise immunity, operating temperature ranges, power supply requirement, and flexibility available. Now, we will consider each of these characteristics one by one. The speed of a digital circuit is specified in terms of propagation delay. Propagation delay is the time taken for the output to change when the input has changed. This brings us to a very important question. Now, as you can see, the input has already started changing over here, and it is at this point when the input saturates. So the question is, which time should I use as reference? That, okay, my input has changed. Similarly, the output started changing at this point and it finally saturated at this point. The question is, what time should we consider as the reference when we will consider that the output has changed? For that very reason, we say that when the input has changed by 50%, when the input has changed by 50%, we start calculating the time. Then we wait till the output has changed by 50%. Then the time gap between those two instances, that means the time between 50% level change of input and output, is called as the delay. In this case, the output is going from high to low. Hence, we will call it as propagation delay for high to low transition, EHL. Similarly, in another case, when the input, this is for a simple inverter, when the input, whatever is the input, its opposite logic will appear at the output. Okay. So here now the input here is again changed by 50% and the output changed by 50%. The difference between those two is called as T propagation delay, when the logic is changing from low to high. Okay. The total propagation delay is calculated as the average of these two values. Okay. And in fact, we have two more terms, rise time and the fall time. The time taken from 10% value to 90% value, the amount of time taken to change is called as rise time here. Similarly, the time taken for the output to change from 90% to 10% is called as fall time. Okay, the propagation delay is calculated in terms of TPHL, TPLH, 50% transition between input and output. Now, speed of operation is a very important criteria for classification of a IC. Faster the circuit operation, we can, based on the construction, whether we are using BJT or we are using MOSFET, or we will see later on that based on different circuits that we will use, we will get different values of propagation delay, and that can be a very good classifier for clubbing the devices in a particular kind of family. Okay. The power dissipation is actually calculated as two things: static power dissipation and dynamic power dissipation. Static power dissipation means the power, the total power, the power consumption when everything has become stable or static. Dynamic power consumption means the power consumption when the states are changing. For ICs, we are considering here the static power consumption, the final state values. That means whatever is the power consumed when the device has settled. That means if I compare our previous circuit, whatever is, so here the values are changing. You can see here the values are changing. We are not considering the power consumption here. We are considering the power consumption during these periods. That means whatever is the power is calculated as V into I. We all know that. So the power, static power dissipation is given as the current drawn from the power supply, which is nothing but VCC into ICC. Here there is an important aspect that the output can be in two different states. One is when the output is at logic high, or when the circuit has logic low. In both the cases, the current can be different because the current path would be different. In logic high state, the current would flow from here, and there will be some capacitance due to the PMOS. Different capacitance value will come into picture, and when the circuit is getting discharged, the different capacitor conditions will come into picture. So current drawn in case of zero logic and one logic can be slightly different, and we take the average of those values as ICC. Okay, collector current. So we call that as VCC into ICC. This ICC is the average of zero state current flow and one state current flow. Generally, we are expecting the voltages in milliwatts. Smaller the power consumption, better is the circuit. Less energy it will take from batteries that we have. Okay, so now based on that, we can have our power consumption. The next point which is used for the classification of devices is the figure of merit. The figure of merit is defined as the product of the power consumption and the propagation delay. Okay, so now you can see this figure. Now, what is the why is this particular value figure of merit important? Then you will see in future that this propagation delay time, and power, they are often complementary to each other. So when we try to improve the propagation delay, that means making it more to make the device run faster, we will end up spending more power. And if I try to save the power consumption, I may end up with a circuit which is very slow in nature. So there has to be a question in which we have to find out that whether we are able to uh, how do we optimize between these two. So the figure of merit helps us to decide those values. So when we see the product of those two things, we will come to know whether it is possible to it is possible to uh, get a circuit which is neither too slow, neither taking too much power consumption. Okay. As we can see that a low value of power speed product is desirable. Smaller this value, that smaller value means propagation delay is also smaller, power is also smaller. Smaller the value, we have a better circuit. Okay. However, it is very difficult to maintain either of two. So we have to decide based on application what is the figure of merit we are looking at. Okay. A very important consideration in making any kind of circuitry is how many circuits am I able to connect with my existing circuitry. Why is this important? Just imagine that you have to take a class. Okay, there is a teacher who has to take a class. If the classroom or if the sitting room allows only for 10 students to sit in the class and there are 60 students in the class, you will have to call 10 students at a time and you will have to take the same class 6 times. So it will be the wastage of energy, in wastage of power, wastage of time. Okay. Similarly, for a circuit, it is very important to see how many circuits of similar type gate it can drive. That means here you can see there is a 2-input NAND gate. There are multiple 2-input NAND gates. And we are trying to see how many such NAND gates this NAND gate can drive. So the question can be, sir, why is there a limit? Why? Because if when we will see the circuit connection, we will see that this current which is coming from here actually comes from VDD and the internal components. Higher the current flow, the device will heat up. So if you connect too many devices, after it reach the maximum capacity, it will not be able to give sufficient current to these devices. Without that sufficient current, these devices will interpret wrong logic at the input. So even though you are trying to give logic 1, but because you have connected so many circuits here, the current which is going to each of these devices is not equal. And some of the device may interpret that this is not logic 1, logic 0, and your circuit will not work. So the fan out is defined as the maximum number of logic gates which can be driven by logic gate output without affecting its performance. It should not heat up this device, neither they should interpret wrong data. Okay. So here the fan out is calculated by the high case logic is I output high and I input high. Okay, maximum input current it can take, maximum output current it can take. And for low level logic, IOL, IIL, IOL, IIL. Okay, and the overall fan out is the average of these two values. So the current helps us to decide now what is the fan out of a device. Higher the fan out, more circuits we can drive, more efficient is the system. But to make a system with higher fan out, your circuit itself can become bulky. So it is not like that we can extend fan out to infinity. There is limitation to everything. Generally, fan in is not a very good marker. However, once we are talking about output, let's consider the input also. So the fan in is defined as the number of inputs that can be connected to a circuit. Here the important thing is that you can see that this is a 3-input AND gate. Okay, so if the if my fan in is small, okay, I will need more number of gates to implement higher logic. That is called as the depth of logic. Okay, so for example, I have to implement 3-input XOR gate, but I have only 2-input XOR gates, so I have to use two different XOR gates to implement 3-input XOR gate. However, another XOR gate had 3 inputs available, so I just needed one XOR gate. Okay, so in here I have 2 gates, here I have only 1 gate. Here the propagation delay will be larger, here it will be slightly smaller. So more number of circuit, it will take more area, more power consumption, and so on so forth. However, here making more number of inputs, it can reduce, it can increase more delay, capacitance, other factors. So it's not always that you can have infinite fan-in. You have to again optimize between the two. Of course, higher fan-in helps us increasing the reducing the depth. That means the number of levels required to implement a logic. However, then there is complementary factors such as speed, power consumptions, and things like that that we must consider. The next parameter which helps us to decide how can we classify the logic families is the operating current and voltage parameters. The current and voltage parameters would play a significant role in the sense that they will also decide the power consumption. They will also decide what is the logic level which we can use without the effect of noise. They will also help us decide the transition levels, so that if in the presence of noise, we can still make the correct decision whether we have logic 1 at the input or logic 0 at the input. So here we have logic levels related with input. We have levels related with the output. Okay. So at the input, we have two important parameters. The lowest level of voltage, which can be considered as the logic 1. Okay, the lowest value which can be considered as logic 1. Similarly, for the lower level for logic 0, the highest value which we can consider as logic 0. Okay, so now here you have see the complementary factors. For logic 1, we are looking at the minimum voltage. For logic 0, we are looking at the highest voltage. Okay, so the smallest voltage which can be considered as logic 1. I request everyone to kindly mute their audio. Okay, now similarly here you have the largest value which is considered as logic 0. The same logic applies at the output. Okay, so we have, see here we have VIH, VIL, input high, input low. Similarly, we have output high, output low, the smallest value. Now the question is Sir, at the input your range is different and output the range is different. Why? Because at the output I don't want to make ambiguity. I want my logic levels to be very precisely defined, very crisp, that despite some noise my output logic high will only be here. So that the decision made by the second circuit, they can make a better decision. Here, because there is very small gap between logic 1 and 0, there is a very good chance that I can make error. Here the gap between the 1 and 0 is very distinctive. I want this distinction level. I don't want my signals like this. I want my signals to be very crisp like this. I want very definitive signals for my 1 and 0. For the input, we may get input from some other source. Hence, we must be ready to handle the noise. That's why I am using a smaller window. I'm giving the chance that even if there is the signal is not very good, I may still be able to function properly. However, when I am producing the output, I will try to give the best possible result. That's the logic. That's why the input, the difference between the logic 1 and 0 at the input is kept smaller, so that even if the input is not that good, we can still operate the circuit. However, at the output, we want our logic to be very, very crisp. That's why the gap is tried to be maintained as very different. Now, these are the voltage parameters. Similarly, we have current parameters. So for the current, we will define as ILs, IIL and IOH. That means the minimum current when we are the when we are the driving zero voltage, maximum current which we can sync. So now I think you must not have heard about sink current and source current. Sink current and source current. For that, we will go back to our circuit here. Here you can see this. Let's see the circuit operation here one time. Here my VCC is going to give the current to the other device. This is called as current sourcing. We are going to source current to another device. But when I am discharging, this current will come and go through our device. This is called as current sinking. We are able to sink the current. So in one case we are supplying the current, in another case somebody else is supplying the current to us. Source current and the sink current. So here in the voltages we are considering what the current that we can sink in logic 1, and here we have sink in logic. We can similarly we can the amount of current that we can source during logic 1 and logic zeros. Finally, this is ICC is the supply current. That means amount of current that we are able, that we have already seen the amount of current it can go on for particular voltage values. Now we have discussed parameters till this point. Speed of operation, which is the amount of time taken for input to change, for the output to change when the input is changing. Power dissipation is the static power dissipation, amount of current flows when the circuit has become stable. Figure of merit is the product of speed of operation and power dissipation. We have fan out, that means the number of circuits of the same circuit level that can be connected, and voltage and current parameters, the minimum input voltages and the maximum output voltages, which help us to declare what is logic level 1 and 0. In the next class, we will study about the the remaining four characteristics, and then based on these characteristics we will see different types of implementations which helps us to classify the digital circuits. We have 5 minutes remaining in this Zoom meeting. Kindly post your questions in your chat. If you don't have a questions, please write down no questions in your chat window immediately. For questions related to fees and other payments, kindly talk after the class. Thank you everyone. Now I will stop recording the session.